Hello everyone. In this video we'll start talking about Turing machines which accept recursively enumerable languages. So of course they are going to accept context sensitive languages. So if I have something like a to the power n, b to the power n, c to the power n, we could construct a Turing machine which accepts this language. So let's see what a Turing machine is. So we have a finite automaton or a finite control, just as we had in our push down automaton. And in our push down automaton we had a stack apart from the finite control, and we could push and pop onto this stack. And in case of a Turing machine, the stack is the part that's going to be different. Instead of a stack, what I have is a tape. So it's called a tape, which has some symbols, and what we can do is we can read from this tape and we can write from this tape. Additionally, we can also move in any direction. So let's just say that my cursor is here right now. What I can say is when I make a transition, I could move the cursor to the left or I could move it to the right. So that's how a Turing machine looks like. And normally what we do is, let's just say that we have 0011 as our string. Then what we do is this is filled into the Turing machine, the tape itself. So let's just say it's instead 000111. So it's 000111. So the tape is initially filled with the input string that's given to us with a B on each side, which is called the blank symbol. So we use the B to mark the ends of the tape, and at the middle we have our input string. So this is what we normally do, and what's going to happen is we could do something like this. We have our cursor right here initially, and then we move the cursor to, let's say, here, followed by here, followed by here. So our cursor is here now, and then we decide that we want to go backwards. So we could also do something like this. We move the cursor here, followed by here, and again to here. So I can move this cursor in both direction when I'm doing any transitions on my Turing machine. So let's see what a Turing machine is going to look like if I wanted to draw the states and transitions. So I have, let's say, a state Q0. From here what I say is, let's say I want to make a transition to state Q1. I see an input symbol from the tape itself. So let's just say that my input from the tape is some A, and then I mention what this symbol should now become. So let's just say that I say that this A becomes capital A now, and third I need to specify what direction I want to move the cursor in. So let's just say I want to move it left. What this is going to do is it's going to look at the tape. So I have my tape right here. I have a B, I have an A, B, B, let's say something like this. And now if my cursor is, let's say, right here, what's going to happen as a result of this transition right here is the following. My new state is going to be, of course, Q1. This is the state that I'll be moving to, and my new tape will look something like this. I'll have a B here and a capital A here, because I said that change the small a to a capital A, and the rest of it remains the same. So I have B and then all of the other symbols, and my cursor will now be at this position because I said that the cursor should move to the left. So this is what a transition or a Turing machine would look like. And the way we write these transitions is that we say that if we have we are at a state Q and we have an input symbol A which is read from the tape, we move to a new state Q prime, and we change the symbol A to something else. So we say, let's say, capital A, and then we also specify which direction the cursor moves in. So we have an L right here. So that's what a Turing machine looks like. And one thing that I would like to point out is that this entire tape that we have here is a read-write memory. So we should be able to read and write at any location on the tape wherever our cursor is. And we'll see what happens when this tape just becomes a read-only thing. So what happens when this becomes a read-only thing is that we are allowed to move in both directions on the input, but we can't really write to the tape. And this is actually given a special name. It's called a 2DFA. So it's called a two-way deterministic finite automaton. And what the expressive power that this gives us is exactly equivalent to what a deterministic finite automaton gave us. So this is just a little more complicated stuff. We move in both directions on the input, but all you need to remember is that a Turing machine tape is read-write. If you convert it to a read-only Turing machine, then that's also called a 2DFA, and that gives you exactly the same power as an NFA or a DFA. That's the only thing you need to remember. What we'll do in the next video is we'll look at how we formally define a Turing machine, how we define the transition function in case of a Turing machine. So we'll do it in the next video. I'll see you there. In the meanwhile, give this video a like, share it with your friends, and hit the subscribe button if you haven't already. See you next time.